The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, thank you, Jeff. I'm Josephine Cheung. I've worked for Grace Construction Products for a number of years with Ara Jeknoforian that many of you know. Ara retired about 6 months ago, so today I give you the privilege to offer you our presentation on the current practice on the use of admixtures to make concrete with low Portland cement content. Okay, so for our outline, we'll talk a little bit about the commercial mix designs. And then the challenges that we see, particularly on set times and early strength. What are some chemical admixture options that we can use to overcome these challenges? How do we minimize set time and strength delay? And then what Mark was alluding to, how do we really keep an eye out for these unexpected cement, SCM, and admixture performance issues? Okay, for us in here, and I'm talking about this high volume fly ash mix, we are talking about a content of about 375 to 700 pounds per cubic yard in the 40 to 60% range. Okay, so I'm really moving up in the cement SCM content. Water cement ratio typically less than 0.4. And in this case, definitely chemical admixtures, particularly dispersing agents, is critical. Set accelerator, because of the set time problem, is also important. And a lot of times when you're talking about in North America with freeze-thaw issue, air entrainment is an issue. You all know about the fly ash. There's a lot of issues with air entrainment, particularly now with the mercury. There's even more issues that we're talking with. But I won't really touch too much on the air entrainment in this talk. So you want to ask yourself, there are so many good points about using of SCMs in terms of increasing durability, lower cost, better sustainability. So why aren't they consistently being used at this high content of 40 to 50%. So once again, we're going back to, in terms of performance, retarded set, strength development, particularly in cold temperatures, and I'll show you some examples of what we're talking about. Inconsistent air entrainment. The first three really are things that I think we can address with chemical admixtures. And as Katifa talked about, the specified mix designs and shortages of quality materials. These are things that many of you have to deal with, but at least I offer you, some solutions that I hope will help us to move from the 18% to the 25% to the 40%. So in terms of the challenges of setting time and early strength, many of you have looked at the picture of the SCM where we are looking at the cement particle versus the fly ash particle. This is a one-day picture where you see a lot of, hydration products being formed on the cement particles already, but barely much on the fly ash. And therefore, it is the addition of these fly ash that we don't have the hydration products. Therefore, we get the lower set time and lower strength. Here is a paper that was given by Eugene on talking about setting time influence with the increase of fly ash. This is not type C fly ash. It's just a name of her fly ash, which is an F ash. At 40% increase or replacement level of fly ash, you can see the set time already doubled. And when you're doing this experiment, sometimes at temperatures lower than about 10 degrees Celsius, you can even see the set time increase to about 20 hours. So what do we deal with it? How do we deal with it nowadays? So in some places, for example, in here, we show you an example of Austin City. How they deal with it is, in hot weather, they allow for higher replacement level. And in colder temperature, the replacement level is really limited. And then some other things that we are looking at when we are dealing with fly ash. In this example, the group really looked at a fly ash divided into 3 different particle size, a coarser fly ash and a finer fly ash content. You can look at this in here. This is the water replacement rate 18% on top, and fly ash level replacement rate. The coarse fly ash in here really did not give us too much water reduction level. But when she was using the finer cement, definitely she see a much higher water reduction level. The reason for that is because in this case, the finer fly ash has more spherical morphology. So therefore, you're getting lubrication effect, and more importantly, packing density effect, and therefore strength increase. So here, I'd like to show you really a series of cases of this mixed design, a 708 pounds per cubic yard mixed design, where we'll walk through how step-by-step increase in fly ash, decrease in water, and the uses of different admixtures, what can they do, okay? So in this case, we have a baseline that has a slump of about 6 inches, set time and compressive strength. When we added the fly ash of 40% replacement level, yes, we saw an increase in slump by about 2 inches, but so does the initial set, right? Now you're increased by 5 hours, which is really not something that we can use in the field, and the strength decreased by half. Now, what we can do is, okay, we say, all right, we can make use of the slump, reduce the water. In this case, we can cut the water by 6%. We did gain a little bit back in set time and in strength, but still, the target is not met. So what are some options that we can do with the use of chemical admixtures, and how do we approach it? So when we think about using of chemical admixtures, there are a variety of different chemistry that we can use. We think about what are chemistry that really can give us the most dosage, or the least dosage to give us the most slump. The reason for that is as you use less chemical in the mix, the chances for it to give you higher sets is going to be lower. And you want to maximize the water reduction to incremental set time, right? You want to have the least set time with the best slump increase, and you want to maximize early strength. So this you can do by designing the correct chemistries of dispersing agents. And then we also need to use the accelerators in this case to really help us get what we need. So this is a chart showing you 3 different chemistries of the water reducers being used. On the x-axis is really dosage of the chemicals to the cement content, and then what is the flow. You're looking at the very traditional use of lignin, where as we increase and increase in dosages, lignin really just maxes out at about 7 inches. But in this same mix, when we use the naphthalene sulfonate, which is what we call the high-range water reducer, you can get more, a lot more. With the introduction of polycarboxylate, what we realize is really we can get to that same level of water reduction or flow with much less amount of cement being used. So the number 1 criteria of how do we use less chemicals to get the most flow can be is demonstrated in here by the use of polycarboxylates. And then if you look at a mix where you have the set time, okay, versus the slump, with the use of corn syrup, lignin, naphthalene sulfonate, and polycarboxylate, definitely for the polycarboxylate, we once again see that it gives you the best slump with the least amount of set time. So what are really all these levers we can put in polycarboxylates? Polycarboxylates are compolymers that you can design with all different type of backbone length, teeth length, and the density of the teeth, and many, many different chemistries that we can use within this chemical. So therefore, there are a lot of levers that we can use to really help us maximize strength or slump gain, or sometimes it's not really just the initial slump gain, but slump life. So a lot of these are really dealing with the design of these different polymers, and then the use of different polymers to get us to what we need. So in here, I show you an example where we are looking at a mixed design that's using a 40% slag. Okay, we are looking at a 0.5% dosage level versus a 0.11% dosage level of 4 different polycarboxylate, where we made this, the concrete at 72F and then cure them at 50, 70, and 100F. So in this case, what we're showing is that there are differences among the polycarboxylates, where they are at the lowest temperature and the highest dosage, you see really the biggest difference. So in here, the cold temperature gave you about a 3-hour difference, and the hottest temperature gave you about 1.5. And in terms of dosage, this is a 3-hour versus 1.2. So we realize there are differences between the chemical response to the dosage and to the different temperature regime. And in here, we show you an example of a slag. All right, whereas in here, we have a 16% slag level versus a 40% slag level. We picked 2 of the chemicals that we had in the previous slide, and you can see that the difference between the 2 polymers at a different slag level is highest when we have more slag in there. So what can we do now, right? Obviously, we can further increase the water reduction. In this case, we use 0.13% of the polycarboxylate 500, which was the best case I showed you earlier. We can realize an 18% water reduction. So a total from baseline of 24% reduction. We gain back some set time, but still it's a 3.5-hour reduction. In terms of strength, we are getting better. We're almost 80% of what we get from the baseline. And by 7 days, we're actually higher than the baseline. So we're getting closer and closer. So what else can we do to make this concrete meeting the targets that we need? And here we show you one example that we got in the field. This is a Portland cement mix. It's a type 2 cement where we were using nepheline sulfonate with a water reducer in one mix versus a polycarboxylate in another mix. In both mixes, we use calcium nitride and some air entrainer. And the results in here is really quite interesting. In terms of slump, we got higher slump with the polycarboxylate. Air, we were able to manage at equal level with the adjustment of air entrainer. Initial set, definitely a lot less when polycarboxylate is used with the calcium nitride. And we also realized a lot higher strength. So there is some synergies that we are seeing between the polycarboxylate and the calcium nitride. And so we come back to the lab and say, okay, is this really real that we're getting so much strength increase in the field? We did a test in here with a steam cure in 80 degrees Celsius. In terms of the calorimetry curve, the heat curve, you're seeing the heat profile is about the same. But at the different times, you do really realize the differences between the strength of the polycarboxylate and the calcium nitride. 34 megapascal in here versus 27, and all the way at about 21 hours, 53 versus 44. So what is really going on? Are we forming some different hydration products? Are we forming are we accelerating the hydration kinetics? Are we making different microstructural changes and therefore also impacting the ITC zone? Are there differences in the pore size distribution, or are there other factors? So we took a project and looked into this. In this case, it's really just a Portland cement that we made concrete, mortar, and cement paste, and did some strength test and some SEM tests to really look at what is going on. So in this case, we have the cement and the polycarboxylate, nepheline sulfonate, and the calcium nitride. All these were actually published. This paper was published in 2005. What we see in here is really, for this mixed design on the concrete, we see with the polycarboxylate with calcium nitride a decrease or faster initial set time, and also a better strength development. The blue curve is the one that has the polycarboxylate. When we're dealing with the mortar and paste, once again, we do see the higher strength in the mortar with the polycarboxylate and higher strength with the paste. This really is just to show you the system that we're using when we're looking at something mechanistically in the mortar or paste that it would reflect that same level of strength gain for the mixed design. So in here, we are looking at the calorimetry of these curves. So the first one, if you can follow me, is this green one. This is the blank, a very, very typical blank mixed design. With calcium nitride, which is an accelerator, you can see the yellow, it gives you the acceleration, no problem. When we add the polycarboxylate, it does give retardation from the blank, and so does methylene sulfonate. Okay, not too much, it's still in a good way. But when we added the accelerator with the methylene sulfonate, you continue to see this retardation, which cannot be corrected. But when you put the polycarboxylate with the K9 together, definitely you do see the acceleration. So what we did was, when we take a look at the microstructure of the polycarboxylate with the calcium nitride versus the methylene sulfonate with the calcium nitride, taking a look at the cement particle, the halide particle, with the spaces in here, you can see the CSH being formed and also the gap. So as in here, you see the black is the gap and the CSH being formed. And when we were doing the just a total analysis of what is the average gap size versus what is the average layer thickness of the CSH, definitely we see a much thicker CSH layer in the Portland cement, in the PCE mix versus the methylene sulfonate mix. And the gap size is also much smaller. So this is critical that we are now seeing these synergistic chemical effects in really giving us a much faster hydration. Same thing as when we're looking at the calcium hydroxide content by the SEM. Once again, the polycarboxylate gave you a much higher amount of calcium hydroxide in this case. So what we see in there was really there is some hydration kinetics differences that is importing between the polycarboxylate and the calcium nitride. So now we want to try this with our mix that has the fly ash in it. So what does it happen? So in here, last time we were talking about this line where we added in the polycarboxylate. Now we added in the calcium nitride. We now are able to realize a set time that's very close to the baseline. We still have 1 hour delay, but very close with the 40% use of fly ash. And the strength also really reaching about 80% of the target. So in this case, at least for our project, we have achieved our goal and was able to use this out in the field. By 7 days and 28 days, you can see the strength is higher. So one word to think about, there are all these different interactions between the cement, the fly ash, the admixtures. So when we tried this type of admixture with 3 different cements that have different alkali content, and also 6 different fly ash that has different calcium content, we can see, okay, that there are differences. What we are checking is really 1 day strength versus reference, and also the set time versus reference. Our target is really to have strength to be 80% at 1 day of the reference, and less than 1 hour for the initial set. In this case, where we have the high alkali cement, we did not meet the target. Okay. When we have the medium alkali cement with lower fly ash content, we also did not meet a lot of the strength target, but getting close. But when we are looking at this area in here, we definitely met the strength. So there are definitely different interaction among these. And so one really has to keep an eye on the interaction of what is happening to cement SCM and admixture performances. And because of this, ASTM already has the calorimetry standard that really is a very, very good tool, in my opinion, when you have something new in your lab and where you have differences in fly ash coming in all the time that could give you differences. This is really a good tool to check. And you would also be using different type of admixtures that is critical to use. And also a subcommittee to be looking at this combination. So in here, really, just one last example we are looking at in here is, this is the ordinary Portland cement with 40% slag. When we add the accelerator, we saw actually the reverse effect, right? We are getting a retardation. when the OPC with slag is added in with a different sulfate level, we do see an increase in the hydration. And now when we added the accelerator with this mix with a different sulfate level, at the correct sulfate level, we actually do see a really good acceleration effect. So until we do this, I think, really it's very difficult, at least for me, to predict what can be happening. So all in all, in here, we want to present to you that the proper selection of admixture systems with the dispersing systems and the accelerators are going to be critical to enable us to use this high volume SCM. High range water reducer through the use of polycarboxylate technology can enable the optimized use of the high volume fly ash. And also, we cannot assume that an admixture system will automatically work, particularly in using high levels of SCM. We see issues with sulfate balance. We see more issues with cement interaction, and therefore the use of calorimetry is really should be our friend. Thank you.